In this topic, we are understanding the organization of the electromagnetic spectrum. So let's take a look at the electromagnetic spectrum and see what it's all about. So generally, we could take electromagnetic radiation and divide it into two different types. We got non-ionizing radiation and ionizing radiation. Non-ionizing radiation is typically low energy. It doesn't have enough energy to ionize atoms or molecules, whereas ionizing radiation does. Now, all of these different types of radiation that you see here make up the electromagnetic spectrum. So in the electromagnetic spectrum, we have gamma rays, X-rays, ultraviolet rays, visible light, infrared, microwaves, and radio waves. You may have heard about 5G in the news recently as cellular technology continues to grow. 5G falls about right here in the electromagnetic spectrum. Visible light is here, ultraviolet light is here, and infrared is here. Now, ironically, the only type of electromagnetic radiation that our eyes can detect, that we can see, is visible light, which falls right here in this very narrow band. So our eyes can only see this type of radiation. Now, there are other animals and insects on the planet that can see other types of radiation, but humans can only detect that type. And of course, there's instrumentation that will allow us to visualize other forms of radiation. Electromagnetic radiation is X-rays. Night vision goggles will pick up infrared. The one thing I want to point out about the non-ionizing radiation versus the ionizing radiation is that these types of electromagnetic radiation are extremely harmful and dangerous to our bodies, simply because they contain enough energy to ionize our atoms and molecules, which results in direct damage to our DNA, which equates to cancer. So how can we relate the electromagnetic spectrum and these things here? Energy, something called wavelength, and something called frequency. One relationship that holds true when we're talking about the electromagnetic spectrum and radiation energy is that the higher the associated energy for a particular type of radiation, the shorter the wavelength of that type of radiation is. So here in this figure, we can see this line. So it's very spaced out over here and very close together here. Well, this line is a representation of the wavelength of the different types of electromagnetic radiation. What it's telling us is that radio waves, which are much lower energy than gamma rays or X-rays, for example, has a longer wavelength than these higher energy forms of radiation. Well, what is wavelength? Well, if you look at this line, wavelength will simply be the distance between two identical points on waves that are adjacent to each other. So these two waves are next to each other. This point and this point are the same points in these two waves, and the distance between this and this would be the wavelength for this particular radiation type. You notice over here, the wavelength for gamma rays, for example, is much shorter than the wavelength for radio waves. The wavelength for X-rays is shorter than the wavelength for infrared. So you notice on this figure that as energy increases, higher energy, the wavelength decreases. Again, as energy increases, the wavelength decreases, and you see that here. Increasing energy as we move across the electromagnetic spectrum from right to left, the wavelength decreases as we move from right to left. So we represent wavelength as this symbol there, lambda. Well, there's another term that helps us talk about the wave-like behavior of radiation and light, and that term is frequency. So what frequency is simply the number of waves that pass through a particular point in 1 second. So frequency is represented by nu, that symbol there. And the units for frequency are per second. So we may see the units as seconds to the -1 or 1 over seconds. You may also see the units of frequency written as hertz, Hz, which means per second. The units from wavelength, because it's a distance, is going to be some measure of length. And you notice here, the units that they use are meters, or if it's much more appropriate to use centimeters, then wavelength can be measured in centimeters. If the wavelength is very small, it'd be appropriate to use nanometers, which is what you see here. Okay. So what is the relationship between wavelength and frequency? Well, the relationship is this. The shorter the wavelength, so as we decrease our wavelength, the frequency goes up. So that should make sense. If I have a wave traveling through a point and I time it 1 second, I will have a higher frequency if the wave looks like this, as opposed to what the frequency would be if the wave were like this. Because again, the definition of frequency is the number of waves that pass through a point in 1 second. The last relationship that we can derive from this is that energy is directly proportional to frequency. So that means if I increase the energy, then the frequency also increases, and vice versa. So let's use this information to fill out this table here in this particular problem. So the first thing we want to do is look at the order of frequency. We're going to take these types of radiation and order them by frequency from lowest to highest. So which one of these 4 types of radiation has the highest frequency and therefore the highest energy? Well, if I look here, I can look at either this table or this table. Gamma radiation has the highest frequency and it also has the highest energy. So I can go back here and gamma is going to have the highest, and number 4, the highest energy, because frequency and energy are directly proportional. Which one of these 4 has the lowest frequency? Well, if I look, I've got gamma rays, red light, blue light, and microwaves. So let's go here. Microwaves falls in this area here. So I'll write in microwaves. If you notice, when we check this table, as I move from ultraviolet to visible to infrared, microwaves falls in between infrared and radio waves in the electromagnetic spectrum. So it would be positioned here. So if I'm choosing between microwaves, blue light, and red light, I see that microwaves here it is. In this small band here, this is visible light. Blue light is here and red light is here. So the wavelength for microwaves is longer, increasing wavelength, than the wavelength for both red light and blue light. So that means because microwaves has the longest wavelength, that it has the lowest energy as well. And because it has the lowest energy, it also has the lowest frequency. So if we go back to this table, let's place microwaves as the 1 lowest energy. Well, microwaves not only has the lowest energy, but it also has the lowest frequency. Okay. When we're looking at blue light versus red light has the lower energy. So it will be next lowest in energy and frequency. Blue light will be here with number 3. what was the relationship that we established between wavelength and energy? The higher the energy, the shorter the wavelength. So let's go back to the table here. Let's find our highest energy, radiation, gamma rays. It should have the shortest or the lowest wavelength. So I need to put a 1 there. Highest energy, shortest wavelength. And the lowest energy should have the longest wavelength. So 4, longest. And 1, shortest. So the next highest energy, which is blue light, will have the next shortest wavelength, and this will have the third. And that completes our table. I know that this was a lot of information, and the relationships at first are going to seem a little confusing. So what you'll have to do is just take a little time looking back over this, looking at the relationships between energy and wavelength, and then seeing in this picture, this depiction of the wavelength, how frequency is also increasing as we move from right to left. So explore the relationship between energy, frequency, and wavelength, and how they correspond to each other as we talk about electromagnetic radiation.